Welcome to this specialized mathematics lecture on surface areas and volumes, designed specifically for Class 10 students. The transition from two-dimensional flat geometry to three-dimensional spatial geometry represents one of the most exciting developments in modern mensuration. Every physical object in our universe, from the minuscule capsule of a medicine pill to the massive domes of modern architectural structures, encloses space and possesses surface boundaries. Historically, measuring these volumes and surface areas was crucial for ancient civil engineering, grain storage, and shipping trade vessels. Today, three-dimensional mensuration is the silent mathematical backbone of industrial packaging, product manufacturing, materials science, and civil infrastructure. When engineers design bottles, container vessels, or structural supports, they rely on combinations of solid formulas to optimize surface efficiency and maximize internal volume. Today, we will master the surface areas and volumes of standard solids and their combinations step by step. Let us begin by exploring two highly crucial three-dimensional solids, the right circular cylinder and the right circular cone. A right circular cylinder can be visualized as a stack of circular coins, forming a straight vertical wall with identical flat circular ends. Its curved surface area, or lateral boundary, is 2 times pi times r times h, and its total surface area includes its top and bottom lids, represented as 2 times pi times r, times the sum of r and h. The cylinder's volume, or internal capacity, is pi times r squared times h. In contrast, a right circular cone tapers from a flat circular base to a single point called the apex. The slant height, L, is calculated using the Pythagorean theorem as the square root of r squared plus h squared. The cone's curved surface area is pi times r times L, and its volume is exactly 1/3 of a cylinder with the same radius and height, which is 1/3 times pi times r squared times h. Next, let us study the geometry of spheres and hemispheres. A sphere is a perfectly round three-dimensional object where every point on its boundary surface is equidistant from its center. Unlike cylinders and cones, a sphere has no flat faces, edges, or vertices. It consists entirely of a single curved surface. The total surface area of a sphere of radius r is derived as 4 times pi times r squared, which is equivalent to the area of 4 complete circles of the same radius. Its volume is 4/3 times pi times r cubed. When we slice a sphere cleanly through its center, we create a hemisphere. A hemisphere has a curved surface area of 2 times pi times r squared, but it also has a flat circular top face. Therefore, the total surface area of a solid hemisphere is 3 times pi times r squared. The volume of a hemisphere is exactly half of a sphere, represented as 2/3 times pi times r cubed. In school algebra and board examinations, we frequently analyze composite solids formed by combining 2 or more basic shapes. Understanding how to calculate the surface areas and volumes of these combinations is vital. For volume, the rule is simple and additive. The total volume of a combined solid is always equal to the sum of the volumes of its individual components. However, for surface area, we must exercise extreme caution. When two solids are joined together, some of their flat circular faces touch and become hidden inside the composite object. Therefore, the total surface area of the combined solid is not the sum of their individual total surface areas. Instead, it is the sum of only the visible curved surface areas of the individual parts. To solve these problems successfully, we must visualize the composite shape clearly and identify exactly which surfaces remain visible on the outside of the combined object. Let us apply our combination rules to a classic problem: a medicine capsule shaped like a cylinder with 2 hemispheres stuck to each of its ends. The total length of the capsule is 14 millimeters, and the diameter is 5 millimeters, which means its radius is 2.5 millimeters. To find the cylinder's height, we subtract the radii of the 2 hemisphere heads from both ends, giving 14 minus 5, which is 9 millimeters. Now, to find the total surface area of this capsule, we look at what is visible. The flat circular ends of the cylinder and the flat circular bases of the hemispheres touch and are hidden inside. Thus, the visible surface consists of the curved surface area of the cylinder and the curved surface areas of the 2 hemispheres. This simplifies to 2 times pi times r times h plus 2 times pi times r squared. Factorizing, we get 2 times pi times r times the sum of h and 2 times r. Substituting our values, we find a total surface area of exactly 220 square millimeters. Having found the surface area of our medicine capsule, let us calculate its total volume. Unlike surface area, the volume calculation is straightforward and additive, as the internal capacity of the capsule is the sum of the capacities of the cylinder and the two hemispheres. The volume of the cylinder is pi times r squared times h, and the volume of the two hemispheres combined is equivalent to one complete sphere, which is 4/3 times pi times r cubed. Therefore, the total volume is pi times r squared times h plus 4/3 times pi times r cubed. We can simplify this by factoring out pi times r squared, leaving the sum of h and 4/3 times r inside the parentheses. Substituting our values where r is 2.5 millimeters and h is 9 millimeters, we get 22 over 7 times 6.25 times 12.33, resulting in a total volume of approximately 245.4 cubic millimeters. Let us study a second classic combination, a solid toy made of a cone mounted on a hemisphere, where both share a common radius of 3.5 centimeters. The vertical height of the cone is 12 centimeters. To calculate the total surface area of this toy, we first find the cone's slant height, L. Using the Pythagorean theorem, L is the square root of 3.5 squared plus 12 squared, which simplifies to the square root of 156.25, yielding 12.5 centimeters. The surface area of the toy is the sum of the curved surface area of the cone and the curved surface area of the hemisphere, as their flat circular faces touch and are hidden. Thus, the total surface area is pi times r times L plus 2 times pi times r squared, which simplifies to pi times r, times the sum of L and 2 times r. Substituting our values, we get 22 over 7 times 3.5 times 19.5, giving exactly 214.5 square centimeters. Now, let us find the total volume of this conical toy mounted on a hemisphere. The total volume is the sum of the volumes of the two individual solids, the cone and the hemisphere. The volume of the cone is 1/3 times pi times r squared times h, and the volume of the hemisphere is 2/3 times pi times r cubed. To simplify the algebra, we can factor out 1/3 times pi times r squared from both terms, which leaves the sum of h and 2 times r inside the brackets. Substituting our values of r equal to 3.5 centimeters and h equal to 12 centimeters, the term inside the brackets becomes 12 plus 7, which is 19. Calculating the remaining terms, we get 1/3 times 22 over 7 times 12.25 times 19, which gives us a total volume of approximately 243.8 cubic centimeters. This is the exact internal capacity of our solid toy. Let us examine a subtractive volume problem. Consider a solid right circular cylinder of height 15 centimeters and radius 6 centimeters. From this solid cylinder, a conical cavity of the same height and radius is scooped out. We need to find the total volume of the remaining solid. First, the volume of the original cylinder is pi times r squared times h. Second, the volume of the conical cavity removed is 1/3 times pi times r squared times h. Since the cavity is removed, the remaining volume is the difference between the two, cylinder volume minus cone volume. This simplifies to 2/3 times pi times r squared times h. Substituting our values of r equal to 6 centimeters and h equal to 15 centimeters, we get 2/3 times 22 over 7 times 36 times 15. This results in exactly 1,131.4 cubic centimeters. Subtractive problems require careful visualization to determine whether components are added or subtracted. Another highly practical concept in three-dimensional geometry is the conversion of solids. In metallurgy and industrial manufacturing, we frequently melt a solid of one shape and recast it into a completely different shape. The fundamental physical law governing this process is the conservation of mass. Assuming no material is lost during melting and recasting, the volume of the new solid is absolutely equal to the volume of the original solid. For example, If we melt a solid metallic sphere of radius r and recast it into a cylinder of radius r and height h, we write the equation: volume of cylinder equals volume of sphere. This allows us to solve for any unknown dimension, such as the height or radius of the recast cylinder. This exact volumetric equivalence is used every day by manufacturers to calculate metal casting molds and design industrial product packaging. Let us summarize the core mathematical formulas we have mastered in today's lecture. First, for standard solids, a cylinder has curved area 2 times pi times r times h and volume pi times r squared times h. A cone has curved area pi times r times L and volume 1/3 times pi times r squared times h. A hemisphere has curved area 2 times pi times r squared and volume 2/3 times pi times r cubed. Second, for combinations of solids, the total volume is the direct sum of the volumes of its parts. However, the total surface area is the sum of only the visible curved surface areas, excluding any internal touching faces that are hidden from view. Third, during the conversion of solids, the total volume remains constant, allowing us to set formulas equal to solve for dimensions. Having these formulas memorized and visualizing combinations is your ultimate key to success in geometry. Thank you for studying with us today. Creating three-dimensional educational whiteboard content like this takes careful geometric planning, structural code design, and formula verification. If this step-by-step lecture helped you visualize combination solids and calculate surface areas and volumes, please take a moment to support our free school learning series. Like this video, subscribe to our channel, share it with your friends, and write a comment below suggesting what mathematical topics you would like us to compile next. By joining our growing digital classroom community, you help us make high-fidelity school science and math lectures freely accessible to students everywhere. Keep studying your dimensions, keep drawing your coordinate wireframes, and we will see you in our next Class 10 Geometry lecture.